It's my great pleasure to introduce you these two outstanding researchers. Just here at the very front, we have Brian Katz. He's a distinguished CNRS research director at the Sorbonne University with a background in physics and philosophy. Brian obtained his PhD in acoustics from Penn State in 1998 and his HDR in engineering science in 2011. His research interests span spatial 3D, audio rendering, room acoustics, human-computer interaction, and virtual reality. Before joining CNRS, Brian contributed his expertise to various room acoustic consulting firms. And then at the podium, we have David Poirier-Quinot. He's a researcher whose current focus lies in sound spatialization perception and room acoustic simulations. You hear the thunder from above. And augmented realities. David's academic journey includes studies in signal processing and computer science. He has a PhD in acoustics, signal processing, and computer science from the Sorbonne University in 2015. David works advances understanding and applications of acoustics in immersed environments. Please note, this talk is streamed, so if there are any questions remotely, please ask them via the Zoom chat. And now I'm looking forward for the talk, Acoustic Twins, Virtual Paths to Notre-Dame. Let's give them a hand.
Hey. Yes. So we decided that we wanted to cover a bunch of things in this talk, so we decided to do it as a pair. So David is going to do the first half, and then I'm going to jump up and take over.
Stop me if I take too long. Few smiling faces, not too many people. I'm used to dark room and scientific talks. Stop me if I'm not making sense, but I'm very happy to be here today. The talk is going to be about acoustical twins, Notre-Dame, and a few other studies we've done. And I'll start with the goal of our overall research, which is basically just simply understand how we perceive sound, spatial hearing, acoustic, and environment. A few examples of studies we are interested about are what makes a great concert hall, for example. And is it true for any type of music or any position in the hall? Or another project of ours was how blind people echolocate. How can they actually estimate the shape and materials surrounding them and even play basketball or just like ride bicycles? And the last one, which is really the one that I'm most interested in, is what actually makes an acoustic simulation plausible, authentic, realistic, various words for various degrees of basically, are you able to tell who's the real clarinet or who's the real person talking to you? And that's what Brian and I are interested in our research. For us, 4 years ago, VR, AR kind of became this huge opportunity of actually designing experiments that were fully controlled in very complex, meaning natural environment where we could just basically be the small gods of our own world and engineer exactly what we wanted to test, such as teleport you from different churches or basically change the single thing we wanted to do because that's how science works. And thankfully, because of visuals and acoustic advances, those worlds became more and more ecologically valid. That word meaning sort of realistic, but as in, it doesn't have to be realistic. It just produces a reaction from the participant that is what they would have done in front of the real thing. I'll come back to that concept. And the first part of the talk is really focused on actually the whole thing, on the concept of digital acoustic twins. And the two main words here are twins. So basically, it has to look like the real thing. But the real interesting part for me is the digital. So sure, it holds in a pocket and these kind of things, but digital means that I can do whatever I want with it. Change it, remove walls, remove things, add things, without anyone bothering me. And that's what we'll see for the two projects I'm presenting. So the ambition of this talk is to present a few workflows that we've been using for research on acoustic and perception, on how to actually create plausible, authentic, realistic digital acoustic twins. And how do you actually get to a point where you do enable natural interactions for your participants to provoke these ecological reactions I've been talking about. And the two projects we present are the architectural design at the Louvre, which I'll use sort of as a case study to present a few concepts that will be handy in Brian's part, which is centered on historically informed performances in Notre-Dame, plus a couple of studies along the way. So, welcome to first part of this talk, now that the introduction is done, which is Project 1, Beneath the Louvre Pyramid. So that started 6-7 months ago, where Louvre people came to us with an acoustic consulting firm and asked for ideas and concepts to make the main hall less noisy. When you spend 20 minutes in it, I think it's 76 dB SPL, something like that. So when basically you spend 20 minutes in it, just going through, it's slightly painful. But when Thank you for that. So when you actually do spend 8 hours in it, as in you do work in the place, it's a nightmare. What you just listened to was a non-calibrated version of it. The real thing is really even more noisy than that. So basic solution would be, well, let's put some foams on the walls or something, acoustic treatment to solve your problem. Two main problems. It's not a regular concert hall, so we can't say it's going to solve every single problem we have. It might be that with less reverberant space, you still have too much noise. So before implementing anything or paying a lot of money for anything, we would like to hear it, because it's hard to judge just based on numbers on paper saying, oh, you will win 6 dB of blah, blah, blah. And the second part is that they have strict constraint on the visuals, because the architect actually had a vision when they designed this hall. And we can't just go, well, paint the whole thing in yellow and you'll be done with it. So they have to have some feedback on this is what we propose, and see, it doesn't ruin the whole visuals of the place. So the obvious solution, you guessed it, was design a digital twin, create something immersive where someone could just be there and judge and say, well, this is definitely worth that many euros, that much euros. So this is the part where I guide you through a bit of the workflows we use for creating realistic worlds. And I use the analogy of visualization because it's oftentimes easier to grasp, but that's just an introduction for later for the acoustic part. So the version 1 of your basic visualization is you just arrive to the place, you stick a 360 camera, and you take a few videos, and then you unwrap that on a sphere, and you're in VR, and you see the place, and it looks more or less like the original one. You do have some sort of digital twin. It's a very simple workflow. There is not much engineering in it, but then it's very static. You can't change anything. You can't change the visuals, the light, the amount of people, because you basically just have a video. If you don't use machine learning kind of things, you can't change anything. And so the version 2 of that workflow is basically you take some time, create a 3D model of the whole thing, and make it fully procedural, populate it with a crowd, and now you can basically tweak everything you want to test the things you're interested in. The only downside of that workflow being it's more demanding, but once it's set up, you're free to do whatever you want. Which brings me to the auralization. So the exact equivalent of your version 1, I stick a 360 camera for the audio, or for the auralization, which is how to recreate an acoustic environment from measurements or simulation, is you stick an ambisonic microphone, which is basically a set of microphone that will allow you to record a 360 representation of the sound pressure in a place. So you stick it somewhere in the Louvre, and then you record, and you decode it on a pair of headphones, and you end up with the exact same type of workflow. It's very simple, no engineering at all. It's very static. You can't change anything. And most of all, for our project, you can't change the crowd, the acoustic, the time of the day, meaning the amount of people in the room. And so you up your game, And that's my 1.5 because it's not exactly the version 2 yet. And you actually start trying to build towards creating a more procedural model, which brings me to the definition of a room impulse response, which basically is just a filter that represents how the room impacts a sound from a point to another in a room. So how it works is basically you go on stage, you go in the Louvre, you stick a loudspeaker and a microphone, you do a sweep, which is a way to excite every frequency in your room. And once you have that, you basically end up with a room impulse response, a fingerprint, name it what you want, a mathematical tool that will allow you to convolve it with any sound that never met the Louvre hall or any room you're trying to simulate. And in the end, you will end up with the exact same acoustical signal you would have had if you did record that sound in that room. So from the whip you just heard, we extract the room impulse response, which is the response to an impulse. We take any anechoic source we want, a clav, a noise, any kind of thing, and we convolve them to end up with, I can place it wherever I want in the room if I did record that room and that position for this source and this receiver. Yeah, that's binaural sound, so it's easier to perceive it on the perfect headphones. But so the concept here is that with this, basically, if you plan things correctly, you can record every source and potential receiver position and then build soundscapes out of after nothing. A few limitations of that workflow are that, well, if you did not record that specific configuration, you'll have to go back. Not that bad, but the real limit is that you can't change anything again. But that brings me to the version 2.3, apparently, of that workflow, read 2 here, which is basically the same as the version 2 for the visuals. You go back to the lab and you actually create the full 3D model for the acoustic simulation. So that's exactly the same as creating a visual model. You've got a mesh with vertices and edges and faces, but instead of assigning visual material to the walls, you assign acoustic materials to the walls. So basically how they will actually impact the sound, how they will absorb different frequencies, how they will diffract the sound. You run your simulation by saying, I'd like a microphone here, a source here, and you basically end up with the exact same room impulse responses I mentioned in the previous workflow. And then you proceed to auralization. It's a very convenient workflow because, yes, it's very demanding to start with, but once you have it, you do end up with a real digital twin you can tweak in every shape and form you want. Of course, when you first design your geometrical model, you do not end up with what we call a calibrated version of it. As in, you run your simulation on that first version of your model saying this is concrete, this is basically plaster. You will end up with room impulse responses that do not sound exactly as the one you recorded. And therefore, when you do the auralization, you will not hear exactly what you should. And so that's where we conducted a couple of researches to actually find a way to quickly at start iterate over the versions of the acoustical model so that we end up with a roughly calibrated model. And we do that based on objective metrics, one of them being, for example, the response time of the room impulse response. If it's too long, you tweak your materials so that you shorten it. And then we proceed to actual perceptual listening tests when we ask 20, 40 people to actually rate a various set of attributes of auralization performed with the room impulse responses simulated in the model until we actually reach the authenticity, plausibility, realism threshold basically when people are not able to tell A, B, X, which is the real, which is the simulated version. And that's basically the step towards this ecological validity I was mentioning. But it's not the final one. Brian will talk about that a bit more, but you do not only have, yeah, you know what, I'll skip on that one. So Brian doesn't know what he has to talk about. I'll end up with so we simulate, we calibrate, we auralize, we find a bunch of anechoic people speaking, we distribute them in the Louvre, we change the various acoustic of the Louvre with, for example, for this talk, the reference, which is your current state, people, and one of the proposed treatments, which is for every surface you see in yellow has been treated, for example, here, with some sort of acoustic foam. Of course, in the final visualization, people will see what it looks like, but the foam itself is designed to look like whatever surface you want. So that's why we just built a very easy visualization so that the Louvre people would actually see, oh, that many surfaces have to be treated. And we integrate all that in a VR application where basically they can just stick the headset and listen to it and have some kind of gut feeling of that works or that doesn't work.
Le musée va fermer ses portes dans 10 minutes. Vous êtes invité à vous diriger vers le central pour emprunter la sortie sous la pyramide. Le musée va fermer ses portes dans 10 minutes. Vous êtes invité à vous diriger vers le hall central pour emprunter la sortie sous la pyramide. Le musée va fermer ses portes dans 10 minutes. Vous êtes invité à vous diriger vers le hall central pour emprunter la sortie sous la pyramide. Nous vous souhaitons un agréable fin de journée. Espérons que vous avez apprécié votre visite.
That video is online, so if you want to actually have the full experience of the binaural rendering and feel of the place. Plus, it also shows the comparison between the on-site recording and simulated recording to show you the impact of the calibration and how close the two are to really call it digital twin. And now that the introduction is over, I'll hand the floor to Brian. Merci.
So what I want to talk about now is the project that we have around the Notre-Dame Cathedral, entitled The Past Has Ears at Notre-Dame. And so this kind of all started about 10 years ago before the fire, and we were on a project of how to improve the use of 3D audio, getting it out of the laboratory and into the general public. So it was a project with the National Radio and the National Television Station, and the National Conservatory to kind of bring 3D audio over headphones to the general public. And we had a chance that at Notre-Dame there was a big concert, and that the choir actually was part of the National Conservatory, so the team that we were with had the rights to record it, and we said, well, this would be a good opportunity to kind of see if we can recreate the experience of this live concert in the cathedral and share it with people who couldn't come to the concert. And this was right around the time when YouTube 360 and Facebook were coming out with their 360 video formats that supported 360 audio. And so we kind of wanted to do that and give the experience not only of what it would be like in the cathedral if you were sitting there, but to kind of show people how the acoustics changes as you move around such a big place. So we did kind of the same kind of tasks that David was talking about in the Louvre. So we have a bunch of sources. Oh, this is supposed to have some cool kind of highlighter. There we go. Let's see. Is that going to work? I don't think so. That may just be too complicated. Oh, well. So basically, we have about 45 microphones to record this big orchestra that you saw in the previous picture. Some of the musicians were up in the balconies, so it was a very spatial kind of composition. It was actually written to be played in Notre-Dame at the time as part of a music competition. Then we have our acoustical model, the 3D mesh, and then we define the trajectory where the camera and the microphone would fly around. We generated a 3D model, a visual model, not too complicated, but to give something to look at during this concert. And then we kind of brought it all together and then made a 360 video. And so here's a bit of an excerpt of that. So you see kind of that highlights how muffled and distorted the sound gets as you get up into different places. So that kind of brings us to the more modern period, and we're going to start and look at this backwards. So in 2019, some of you may have heard, we had a bit of a fire in Paris, and the cathedral was highly damaged. And in the reconstruction process, the state came out and said the goal for this reconstruction is to make it like it was before. And we thought that was kind of interesting. If you kind of look at the history of Notre-Dame, you can see that it's gone through a lot of architectural evolutions, a lot of decoration evolutions. And the idea was if you kind of look at the whole timeline of Notre-Dame, you can see how this is the building that was there before Notre-Dame that was also probably exactly on the same site. And then over a couple hundred years, you see kind of the evolution of the construction of this architecture. And at the same time, you have these evolutions of different musical styles happening. And then you also have the introduction of the organ into the cathedral that then gets moved progressively from the choir end to the far end. And then you also have some other historic events like revolution that also impacted the cathedral and several restorations over the periods of time. So we kind of got interested in looking at how all of these things change and what is the impact on the acoustics. So we're kind of taking an idea out of the archaeology field of research, which is called experimental archaeology, which is basically learning about history through doing or trying to repeat something that other people have done. And then combining that with kind of the high-tech methods that we've been developing, we end up with something that we're calling experimental virtual archaeological acoustics. And the idea is to use virtual simulations to put people into situations from the past and see how they react, and kind of to learn from that. So we take that calibrated model that was based on the example that we did about 10 years ago, and then looking at documented evidence of all the changes in Notre-Dame, we basically deconstruct the building bit by bit to arrive at all of those previous states. And then we can build a VR simulation and then put you inside that. And some of the things that we've looked at, for example, are how did the changing acoustics affect the evolution of music composition? Or how did the changes in preaching language from Latin into local language in French change the requirements of where the preacher had to be situated? Again, how the organ's evolution of its position affect organ music composition and what could and couldn't be heard inside the cathedral. And then how did other changes in church practice, like decorations at high festivals, affect the acoustics of the space? So to do this, we brought in a big group of interdisciplinary researchers from acousticians, computer scientists in virtual reality, musicologists, historians, architects, sound engineers, religious sociologists, and I probably forgot one or two. And so we've been working on this for about 4 years. So one of the big studies, for example, is this evolution of musical style and looking at how this emergence from monophonic singing to polyphonic singing, which is occurring at Notre-Dame and right at the moment when the building is being built. And so the idea was to kind of look at, are one of those architectures better suited to different kinds of singing, and could that have been some of the rationale behind the ability to create these new forms of singing that weren't possible in previous states. So we put together a system, so it's a real-time virtual system where we can have 4 singers standing in a studio together and actually change the room acoustics around them. And we're able to achieve enough low latency and enough transparency that they should be able to sing as if they were singing naturally inside the cathedral as it's changing. And then we can use kind of analysis of how they're able to sing, their posture changes of how they're singing, questionnaires about how they're singing, and also having other people outside listen to those performances and judge what is the impact of those kind of changes on their singing style. So at the moment, that kind of analysis is underway, but one of the key things I think we have is in the interviews where this group of singers had actually sung in Notre-Dame before the fire, and one of the comments they came back and said was, "We have just as much difficulty singing in your VR system as we did at Notre-Dame." And for me, that was a clear justification that the system is actually ecologically valid. We're not aiming to make something that sounds good. We're trying to make something that sounds right. And those are kind of little different aspects. So basically, they did that for about 2 or 3 days, repeating the same songs over and over and over, and we're changing the acoustics and changing the layout. And as you can see, for example, some of the singers, they're kind of flowing and moving, and you notice that when the acoustics gets more difficult and they have a harder time singing, their posture gets more rigid, or they start looking at each other more and more for references, for synchronization. And all of those things are what we're kind of bringing into the analysis of the ease of performance, and to see if there's a relation between that and the acoustics. And then, so from these kind of research, so that was just one example. We've been doing a lot of different things. But with the kind of world visibility of Notre-Dame and the interest, we've been thinking a lot of how to kind of share our research with the general public. So while the previous little virtual tour that we did was kind of an afterthought that had not a lot of budget, for example, in this project we kind of thought about it early on of, we really want to be able to share quality productions with the rest of the world that may not explain in detail everything that's coming out of what we're doing, but at least give some hints, and for those who are interested, they can go further. So the first thing we did, that was a year ago, we produced a radio fiction, and basically we went to a production company and said, we are interested in communicating these 10 bullet points. Write us a story that kind of gets people's attention and interest. And the result of that was this 4-part miniseries called Looking for Notre-Dame. That's a fiction around Victor Hugo while he's writing the Notre-Dame novel, and he gets writer's block and then gets visited by kind of a muse who then teleports him into the past. But basically everything that he's experiencing is happening in the digital acoustic twin of Notre-Dame. So we're always bringing those acoustic elements and then kind of traveling through history and seeing how the acoustics is changing, his interactions with his editor in Notre-Dame where they're yelling at each other are all resonating in Notre-Dame. So just little bits to kind of get people's interest. And then the second, which is something that we launched in the beginning of May, is a virtual museum audio guide around Notre-Dame. At the moment, we can't go in. It's closed until this December. So the idea was to make kind of a virtual tour around Notre-Dame, but where you could listen to what's happening inside Notre-Dame and throughout history. And depending where you're standing, if you're near the bell towers, there'll be a piece about the bell towers. If you're near the choir, it'll be about the choir. And so we worked with a team that did that. So that's now available in 3 languages. And it's free, and we've had, I think, about 1,000 downloads already. You can also do it at home. Without the GPS, you don't get to see Notre-Dame. But again, the idea is to kind of communicate about a dozen different ideas to the general public in kind of an entertaining, ludic way, and then have pointers to websites and things on the journal articles. And then the last bit, which is one that we're in the middle of producing now, is looking really at the evolution of music around Notre-Dame, and to kind of present a concert, or a virtual concert in this case, spanning 8 centuries of kind of music evolution and architectural evolution, where basically we take studio recordings of musicians, and then each one is placed into our virtual acoustic model of Notre-Dame at the place where those musicians would be in the acoustics of when that would be. And then kind of interlaced with a bit of documentary to kind of explain things, and then you add a really some good high-resolution graphic simulations of what's happening, and then the idea is we're going to make a big film out of it that comes out at the end of the year. So I have a little clip of a work-in-progress version on it, so there are kind of some faults in it, but just to give you an idea of where we're going. There we go. So I will say that that example didn't have the acoustics of Notre-Dame in it yet. It was a test on the video rendering. So if it was very clear and audible, you got lucky. So I want to kind of conclude with the list of the people that have involved so far, between the group of acousticians, the group of other specialists, all the musicians that have been involved and kind of donated their time, the access that we got through the cathedral and the restoration. And then here are links to all the different kind of demos and the examples that we've done. And now we would be happy to take any questions you have. And since we're at the end, there's no time limit, so just keep them coming.
Thanks for the amazing talk. Are there any questions?
First, very interesting. I'd have 2. For one, you said it's a lot of work to make the models. Imagining Notre-Dame, like how many 1,000 hours are we talking? And secondly, you mentioned that you then having the model, even with the basically just concrete, or in this case, marble and stone, you still need to tune it to get to a right behavior. How do you do that if you then go back in history? Do you find like other churches which are from the same period so you can do the tuning, or how is that achieved?
Okay, so the first question, I don't know how many hours. I think it was estimated, I think it was about 6 months of work for the student and an intern to generate the first version of the calibrated model. And that was before the fire. And then after the fire, another student came in and added another level of kind of rigor and detail, and she probably spent another couple months fine-tuning it and adapting the model so that it would be easier to go back in history because the original model was just meant for Notre-Dame at the time. I forgot now what the next question was. The adaptation to different, so basically when you do an acoustic model, you end up doing a lot of simplifications in terms of geometry size. So for example, I could do that whole wall and say it's concrete, but so is that. So there's the fine detail of the texture of that concrete that's different than this concrete. That also has, a table and an air conditioner and some other detail. So you kind of end up fine-tuning a global view of all the different materials into a single kind of material definition, if that makes sense. So you tweak, you calibrate relative to the reference of what concrete is to the specific instance of the installation. So that we did with, I think we probably had a couple hundred measurements that we did in Notre-Dame, and you kind of try to optimize the results for all of those. Once you have that, then to go back in time, well, one, you've already figured out what the material is. So in the beginning, you're doing a lot of geometry changes, right? You know that you can assume that the stone of Notre-Dame now is the same stone that it was 100, 200, 300 years ago. You do use references from other churches that have been measured. David showed up an example of us going to the Louvre and actually measuring tapestries at the Louvre, with the idea that there were moments in history where there were tapestries in the cathedral. So then we actually have the data that we can use directly in there. But it's a lot of educated understanding of how the kind of similar materials work. The base model for what the church was before Notre-Dame is based on an existing church in Italy that's roughly the same style, but not necessarily the same size. And there was already a team in Italy who had made a model. So basically we replicated their model and their measurements and then morphed it to the same size as the one that was in Paris. So the idea is always to find a concrete reference, not concrete, but a solid reference, and then work like within regions of that so that you have a stronger confidence that it's doing something sensible.
Thank you for your talk. I would have a question, maybe rather to the first part, but I'm happy to get any answer of you. In the first part, we heard that these toolings are often used to optimize the behavior, the acoustic behavior of rooms. So you model it, you make a prediction. Have you ever measured after the prediction, so your tools, you say, okay, put this there and there, have been installed, and have you measured the room after this has been installed to verify how close or not close your prediction is from the real outcome you have after installing all the measurements?
Well, you did work for acoustic consulting, so...
Yeah, so those kind of tools are used a lot in kind of room acoustic consulting. I remember trying to do that a few times where you've predicted it and then you want to go in and see. And the experience was typically that between the time you say what it should be and all the kind of the design iterations through the engineering departments and what actually gets built, it's not what you said it was. So to have an example where you actually have it, done the way you meant it is rare. And in the consulting world, being allowed to go in again and do more measurements, usually consultants like to be paid. And as far as the building is concerned, they got what they asked for. So they don't need you to come in again and do more. But there are instances of those kind of measurements being done. Usually on very big buildings like high-end concert halls. The use of them is more to establish what the result was, not so much as a reference to how the computer model 4 years ago predicted what it would be. But there is a lot of work in the field of the simulations on their accuracy. But usually on test cases, not on actually built situation.
My question is, you showed that you can bring the acoustics of a church or of other buildings into the lab, for example, so that the singers have the feeling also to be in this environment of the church. I could imagine, as it's sometimes difficult in a church to sing together, to play together, that it would also be possible the other way around, to make it easier for the musicians in big churches to play together. Did you ever consider doing this in a live concert for them, for example?
There's kind of two things there. One is adding the reverb to a live performance. So we have been thinking about that. Removing reverb is a very different prospect. I mean, you're kind of playing with entropy in a way. It's always easier to add than subtract something. Most of the noise control systems don't work in 3 dimensions because there's too many unpredictable paths for that noise to be there. I mean, in a church, what usually happens is, well, I'll give you a microphone and I'll give you a speaker, and you kind of battle it that way. But no, I don't think I've ever heard of an active reverb removal in a live performance.
But it would actually be a quite interesting project because it's like kind of simple to imagine a noise cancellation headphones, direct feeds to each other. But then the question is, what type of reverb do they actually hear so that they actually create music that do fill the space? I think it's possible, but I'm thinking it's also part of the performance to actually, I'm 10 meters away from you and it still should sound as in we're feeling something, and otherwise people in the public will just be, and we'll have like private fun and you will have like some kind of lame concert. But that, yeah, I would be interested in doing that.
It's usually better to suit the music to the acoustics of the space than...
So, thank you so much. I wanted to ask, so you said that, the sound or the acoustic, they wanted to have it from Notre-Dame like it was before. So, but do you know what kind of before they decided on? So you said that...
Well, that wasn't even just about the acoustics. That was the general order from President Macron, which was build it the way it was before. And I think in most sense they meant the day before the fire, we want that, except we want sprinklers. And then they started adding a bunch of other things. But I think the vision was pretend like it never happened, but fix it. And we've been trying to look at it by saying, well, maybe that wasn't the best time in history to target, depending on what the use is. I mean, we had the same team that we're in had done measurements in Notre-Dame in the 80s, and we see a change in the acoustics between the 80s and before the fire, because they installed carpeting in parts of it to reduce noise from tourists. Well, that's gone now. So the question is, do you put that back in or do you put something else in? And we've been talking to the cathedral about that because the problems, the types of noise that tourists made in the 80s, they don't think is the same type of noise that people make now. So in the 80s, tourists wore hard-soled shoes more than tennis shoes, because tennis shoes were kind of the youth and not the general public. So there was much more clack, clack, clack. Now everybody wears comfortable walking shoes. But now they're all taking photos and they're all talking more. So we actually need to look at how could you reduce spoken noise versus footfall noise. And so it's kind of vague, but we're trying to get in there before opening to look at new ways to make it the way it was before. I mean, we even went to the choir and said, well, you know, the music that you're singing was actually in a different acoustics of Notre-Dame, and maybe you'd like to have that kind of acoustics instead of this one. And kind of their response was, no, we're going to get a better sound system so that we don't need to worry about that.
Thank you for the amazing talk. My question's actually building up on the question my colleague asked. So
I don't know which is your colleague. It could be all of them.
Most of them are my colleagues. So you said you want to rebuild, or it should help to rebuild Notre-Dame. So how can your acoustical twin add to that and help to reconstruct the acoustics. So do you set your acoustical twin on fire and rebuild it up, or how could that help?
We didn't do that. I mean, we did take the original model and then punch holes in the ceiling where the vaults had fallen through, and then did measurements to kind of further improve the calibration of the model. But the idea is that we can look at the effect of propositions by the architects and the restoration team and see what those would be. So kind of early on, before the restoration kind of concept was kind of nailed down to this, make it the way it was before, there were kind of architectural proposals that were quite wild, you know, a glass roof with a park on top and things like that. So that's quite easy to integrate into the digital model and say, well, if I replace the stone arches with glass, what will happen? So any kind of proposition, you're able to kind of modify and update the digital model and see what the effect of that is. The most concrete example that we've had in the restoration so far was with the choir organ, which was destroyed. The main big organ just got basically dusted and had to be cleaned, but the choir organ was destroyed during the fire. So they wanted to replace it, but they also wanted to make it bigger and better, you know, not like it was before, but the way they wanted it to be. So we actually got the proposals from the 4 organ builder teams that were selected or like shortlisted, and put their designs into the model to see how those affected basically the extent of the projection of the organ sound and how loud it was and how intelligible it was in different places, to kind of help the design team judge which one they wanted. So it wasn't based only on that, but that was a request from the reconstruction team. The next one will probably be looking at solutions to kind of the footfall noise and the tourist noise, to kind of make some proposals of, you know, this may work, this may not work, and try to help it out, kind of test different propositions that way. So if you put curtains here, what would happen? If you put carpet here, what would happen? Because it's cheaper to do it in the model than it is to buy it and then change your mind.
Okay. In this case, I would say the time is also over. Let's thank the speakers again for the amazing talk.